Hello learners and welcome back to VLSI Simplified. So in our VLSI journey so far, we have explored how a design is structured, how modules works and how to connect them. But now we are moving to a very important layer, the signals and data types which makes everything work. But before we jump into a keywords like wire or rich, we need to understand what's happening underneath. So let's discuss what we are going to learn in this video. So in this video, we will cover the types of signal values in Verilog like 0, 1, X and Z. What signal strength is and how it helps resolve driver conflicts. And a practical ModelSim simulation to visualize the signal value resolution. And finally, how all this sets the stage for learning wire, rich and other data types in upcoming video. So by the end of this session, you will have a solid grip on signal behavior, which is the foundation for everything else we'll do in Verilog. Alright, this is VLSI Simplified. Let's get started and let's simplify.
Tell me like a Hellcat.
When you are working with Verilog, you are not writing software. You are describing an actual hardware behavior. So, and in hardware, everything is driven by signals. They represent voltage flowing through wires, connecting logic blocks and triggering operations. That's why understanding how signals behave is absolutely crucial. If you declare the wrong signal type or misunderstand how it interacts with others, you can end up with the wrong simulations or worse, hardware that doesn't synthesize or behaves unpredictably on silicon. So in this video, we are laying that foundation. We'll explore the possible signal values, their signal strengths, and even look at how these signals interacts through a small ModelSim simulation. Trust me, this one step will make learning wires, registers, assign and everything else so much easier. When we think of binary systems, we usually think of just 0 and 1, right? But Verilog is a hardware description language. It simulates the real electronics, which are often more complex than that. That's why Verilog uses a 4-valued logic system. That is 0, which represents logic low, 1 is logic high, X stands for unknown. This could be due to uninitialized signals or when two sources try to drive a conflicting values. And Z, which means high impedance, or in other words, no one is driving that signal, just like an open circuit or a disconnected pin. So these two special values like X and Z are really helpful for debugging. For example, if your simulation shows an unexpected X, it's a sign that something went wrong. Maybe a signal wasn't initialized properly or you forgot to assign a value in some logic path. And Z is used when we want to model a shared bus or tri-state drivers. So we will look at that in action very soon. Signal strength. Here is where things get interesting. So Verilog doesn't just stop at signal values. It also lets us define how strong a value is. So imagine two drivers trying to assign a different values to the same wire. How should Verilog decide which value wins? That's where signal strength comes in. So there are different levels. Supply 1, supply 0. They are very strong like hardwired voltage sources. Then strong is used for logic gates, what we typically see in most RTL designs. Full strength is used for weak pull-up or down resistors. High Z is the weakest, meaning the signal isn't actively driven. Now, this doesn't affect synthesis in most practical designs, but in simulation, it helps Verilog resolving conflicts and show you what would really happen on silicon if two drivers tried to take control of a single net. And in our ModelSim example, we will see how exactly this resolution plays out. So in this part, we will quickly jump into ModelSim and demonstrate a simple test bench to show how signal value conflicts are handled in Verilog. We will connect a single wire to two drivers, each assigning a different values like 0, 1, Z or X. So this will help us to visualize how Verilog resolves conflicting assignments. We are not going to explore all signal strength types here, since they are not synthesizable and mostly used for simulation purpose. Our focus is purely on how signal behaves during conflicts and what the waveform looks like. Let's write the code and see the output in ModelSim. So here is our example. So here I have a module where I have declared two register data types, that is driver 1 and driver 2, and wire data type bus. To this bus I am assigning a value from driver 1 as well as driver 2. So these two drivers will create a conflict in bus. So in the initial begin, I am assigning the value to driver 1 and driver 2 and I am keep on changing the values for every 10 nanoseconds. So let's see what happens in the simulation. Let's compile first. So you can see compile was successful. Then start simulation. So let's run this. So if you zoom in the waveform we can see the values for driver 1, driver 2 and bus. And in the console you can see the values. So in the waveforms you can see how the conflicting values behaves and what is the output. And in the console they can see the values how it conflicts. So if you are driving the same values like 1, 1 and 0, 0, the value output value will be the same 1 and 0. If you are driving conflicting values like 0, 1 and 1 and 0, the output will be unknown because both are having the same strength, so it's giving the unknown value. If you are assigning unknown value to one of the driver without checking the another driver, you can expect the output will be unknown. If you are driving high Z to any one of the driver, the output will be the another driver value. So high Z with 0, 0 comes. High Z with 1 and 1 comes. So here is the conclusion. So X is the superior. So any value with X will be the output. C is the least superior. So any value with Z, the other value wins. 0 and 1 are equally superior. So driving both at the same time will lead you to unknown. Alright, we have now taken our first major step into Verilog. Have learned what the signal values like 0, 1, Z and X means and how they appear during simulation. We also touched on signal strengths and saw how Verilog resolves signal conflicts using ModelSim. This is the base you need before diving into actual data types like wire and range. And that's exactly what's coming next. We will explain each of those types with examples and waveforms. So make sure you subscribe to our channel so you don't miss our upcoming videos and turn on the notification. See you in the next video. Bye.